All right, hello everyone. We are doing a physics project working session, except it's actually about metamathematics, but it's using ideas from physics. And apologies for starting late. I was giving another talk and there were lots of interesting questions. And I always learn much from questions. And this was no exception. All right, let's talk about metamathematics. The thing that we're really trying to do here, this is sort of a subpart of a bigger project that hopefully will see the light of day in the next few weeks. The subpart has to do with understanding sort of how to make the best kind of low-level model of the mathematical process and of mathematical axiom systems. And what we're looking at here is pure substitution of these two-way rule structures with in which, well, what we were trying to do most recently was, given the rule A dot B is equivalent to B, that rule can be used here. Let me go ahead. That rule can be applied to itself to get other kinds of rules. For example, we could derive the rule A is equivalent to A blank is equivalent to A blank, and it's a little bit different because there's canonicalization. And by the way, we need to figure out what letters we're going to use. I think, Nick, you've picked ABC for the canonicalized letters, and I think you're probably right to pick those. And I have been using XYZ to define my rules, and I've been using ABC as constants, and that's probably wrong. And I don't know, maybe it would seem too technical if we use alpha, beta, gamma as constants. But I kind of think we have to use something different as constants from the things we're using as letters, and it seems very wrong to use XYZ as constants.
Yeah, I agree.
They're the quintessential variables.
I mean, so I don't have a problem with alpha, beta, gamma, but I might not be representative.
Yeah, I think we have to probably go to that. I don't think there's any choice. All right, so the thing that we were looking at yesterday was trying to understand how proofs arise. What is a proof in the structure? And Nick had done some nice work here. Let's pull it up. Nick always has a more recent version of our system than I do. Okay. All right. So, what is this? So this is, okay, so what we have here is going to be we're using the axioms A dot B is B, rather trivial axioms. And we're trying to establish from that this theorem here. Oh, wow, you've changed the theorem. Is this a different theorem?
Yes, I have commented out like another two candidates there. Okay.
Does it matter much which one we look at? I mean, this one looks nice.
Well, I was just trying one where I have like an event that has the same input twice, somewhere in the middle.
Okay, that's nice. Okay, well, fine. But let's see. No, I do not need that. Wow, that's an interesting bug. Some random piece of software updating itself on in the middle of my screen. It's rather rude of it. Anyway. Okay, so does this occur in the level 3? If we just start off from A dot B goes to B, does that theorem occur in the 3-level in this thing here, does that occur?
Yeah, that's the same thing. That's 3 steps of your evolution.
Okay, so this theorem does occur here. Yes?
Yeah, because I used the same one, the same graph.
Okay, fine. Oh, I see that. There's your graph. And what is the labeled one?
That's the same, but just with the token labeling true. That's it.
Okay, fine. Okay, so I have to run this anyway. Okay, so then we should be able to indicate where that. So this thing here is the future light cone of that statement, correct? This is the future light cone of that. The whole thing is the future light cone of that.
Yeah.
Yeah.
Right.
The entailment cone, but yeah.
Right. Yeah, I'm sorry. Maybe I've done too much physics. The entailment cone, proof cone, whatever.
Yeah.
Okay. So then okay. So now the theorem is somewhere down here, presumably. Right, but
Yeah.
a lot of this was irrelevant to making the theorem. So let me just make a Metamathematics 30 here. And make it bigger so people can see it. And then I want to start. Okay, so this is our, so TEG, if I look at TEG, let's just copy that over here so I remember it's there. And if I look at TEG, it should be that giant graph. There it is. Okay, so now the theorem that you are picking, and that theorem is this thing here. And we could say highlight graph TEG, comma, this thing here, and let's say style of that red. Point size. What's a good point size? 0.01. Oh, stupid bug. Is it going to work? By the way, have we reported this bug, by the way?
Nick, did you report it?
No.
Okay.
Can we, maybe somebody who's on our live streaming team could screen capture this and report it? All right, I'll do it.
It's still unclear where it's a bug or a feature. So what we're trying to highlight there, a vertex or. Okay,
but so we can, if we do an edge fix on TEG, this will work, right?
Yeah, on the vertex itself, the two-way rule.
I know, but we also need to edge fix the graph.
Yeah. And two-way rule fix the vertex. Yeah, right.
And now we're going to find that point size designation is wrong. But oh, there we go. Let's make it a bit bigger. Okay.
All right.
That's cool. So so our goal is to prove that theorem, and that theorem is a naturally occurring theorem.
Yeah, it resides in the entailment cone.
Yes. Okay. So now What's the most direct way to prove that theorem? So Nick now has this result. What just happened? Oh, it opened something up. Okay, so let's just reprove that. Brilliant. Okay, so can we draw that as a piece of something that looks like this, or is that not easy to do? Is there a way to format this?
I've done that.
Oh,
just at the bottom, right?
But that's a subgraph as opposed to, oh, wow, look at that.
Yeah.
Cool. Okay, you've already done all this stuff. Okay.
It's just one problem with the subgraph that I don't currently understand. It's like if you compare the proof, like graph of the proof and the subgraph, it has some redundant edge there.
Well, it has an edge that's not in the full graph, but it's in the subgraph, right?
It's not in the proof. It's not in the proof, but for some reason it's still a part of my subgraph.
Mm-hmm.
What do you mean? Which edge are we talking about?
Just compare this one to the graph of the proof, just a list of edges. Like
wait, why are there these two outcomes from the, is that because the event has been deduplicated?
No, this is correct, because one event can generate multiple tokens. We have substitution lemmas, right? It can generate multiple tokens because it can substitute at different positions.
Mm-hmm.
Yes, that's right.
Let
me just think about that for a second. Okay, so wait a second. That's saying, why isn't that two different events? Why is that this is the self-application of that lemma, right?
Yes. It's one call to the substitution lemma function. So it's one event.
One call.
But what happens? Okay, let me understand that relative to strings. If this was a string rewrite system, let's actually make the analogous string rewrite system just for fun. So it will be, I mean, it's kind of weird. AB goes to B and B goes to AB. Okay, and I don't know what we're starting, and let's say we're starting it from AB and B. I don't know how analogous this is going to be, but we can at least try it.
Wow.
That's not very helpful. Anybody think of how to make that better?
Well, it's not accumulative, so it's not anything clear to analogous.
Okay, so how to make a string system accumulative?
Well, I mean, we could do that by putting an X, by putting an arrow effectively there, and by saying, it's not going to work. It's not going to work. I mean, but we could make it accumulative by just having a special character in the middle, right? We could say AB, you know, basically arrow B, for example, and we could treat that as a string.
As a string.
And then we could apply, how would this work? Actually, we could do it with a string, with a system that it's always pairs. What would that look like if it was just LHS, RHS, and we're always, how would that work? Would that not just work with strings? So the rule would be, we're applying to the left-hand side. Yeah, why isn't it just this? Why isn't it, okay, Okay, so let's
say to have like some kind of special meta rule that takes as input this character with the arrow and another string and applies them together. I think it's not clear.
No, but what we're saying is, no, look. What we're saying is this. Every state is LHS, RHS, okay? And the rule of application is LHS1, RHS1, and LHS2, RHS2. And then we just do substitution on that. We just say, let's just try this. Let's just try this. We can do this. So what we're saying is, I don't know what we call this, but something like string apply, and then it's LHS1 being applied to LHS2. And then, and I don't know whether we want to do the flip around as well. But let's see, so this thing would be a string replace list, if I'm not mistaken. I know which way around we're doing it, but in LHS2, string replace list mapped over, okay, so it's LHS1 arrow RHS1.
Okay.
Mapped over no. What this is LHS2 of this, and that's going to give a bunch of results. And then we want tuples, exactly. Tuples of this, am I getting it right? Comma, is that right? Comma, the corresponding thing with RHS2.
Yeah.
Okay.
So let's just check whether this is working. So string apply of, let's say, A, B goes to B. Actually, maybe the better way to represent this is in terms of, let's change this. Let's do it in terms of rules.
Okay.
Okay, so here onto the tuples, we'll need to map. We'll need to do a rule triple at this. Am I right?
Yeah.
That's not good. Okay, string replace list LHS1. Why does string replace list of AB goes to A? What the heck? Did we get something wrong with our tuples?
Nick, what do you think?
Let me remind myself what tuples does for.
Maybe you don't have to wrap it in list, right? Oh, wait. No, we do.
That does the right thing. Well, let's just return the tuples there. What?
Okay. So some of the replace list returns an empty list. That's the only explanation. So applying this to the right-hand side to somehow an empty list. To A. Right?
No, to AA.
To AA. Yeah.
Oh, that's obviously it's obvious why that happens. But is that what we want? No, we don't want this. We don't want tuples. We want. Oh yeah. Look. We want the original as well in each of these. In addition to the string replace list, we also want LHS2 in this, right? Because it could be unchanged.
Right. Yeah.
Okay.
Okay, that looks okay. All right, so now, drum roll. Oops, we now want to do the rule triple at.
Okay. And
there we have it.
Ding, ding.
Okay. Okay, so now, if that was like ABA, okay, fine. Now we want to have the two-way rule version of this, which is that the two-way rule version. Let's write out the two-way rule version of this.
Okay.
So this thing goes actually we can already do non-trivial things here. So maybe we should. Let's just see what happens with some one-way rules in this case. So what we want to do is multiway. I think we want to say multiway function system, although that function really needs to get rewritten.
Yeah.
Okay, so now that's going to be string apply. Is this right or is this not right? We want an accumulative thing, right? Nick, how do we make an accumulative thing? Because multiway function. What's that?
I thought your plan was to use this special character, then like split it like each time and apply your function.
That's what I'm doing. That's like what string apply does.
No, but actual character arrow within your strings. Like you use the multiway system and a string substitution. You have
I know, but you don't need to do that. But we're just, the states are rules now. See what I'm saying? The whole state is a rule now, and that's equivalent to that. We don't need to embed the character in the string. I claim this is just doing what time?
All right.
Okay, so now here, onto this. Yeah, maybe we can do it with this. We just need to say, given a state. Wait a minute. It has to be done with a token event graph, doesn't it? Because this is a state with a bunch of tokens.
Yeah.
Right. So what's going to happen is each one of these is going to pick up one, it's a token event graph because it's going to, every one of these things is paired with one from the other. Isn't that right? I mean, everyone, look, a given, this is a state here. We're starting off from this state here.
Okay.
Yeah. Look, we can clearly do something. I think we can do this with one-way rules, right? We can basically say we're adding to the state. So we're adding that left-hand side. So what we're doing is we're saying, okay, so this is the naive thing we're doing. We are saying nest list of prepend hash, comma, string apply. No, join that to the string apply of the thing with itself, if I'm not mistaken. And then we apply that to a rule like A goes to AA, and maybe also
another one.
AA goes to A. And then let's do that for 2 steps. Oh, what the heck? What's going on there? String apply of hash to hash. Let's find out what that was. Oh, the string apply needs to be outer producted over those 2 things. Is that right?
Yeah.
It's like this, and then we might as well say flatten this. And then do we want a union here? We probably do. Okay. That seems right. Wait a minute. A goes to A. What happens if we just go A goes to AA? Why does it work that way? A goes to AA. Oh, because it can apply to both sides. And that's why it can get AA goes to whatever. This is kind of an interesting type of system. I've never looked at this before.
Yeah, it's interesting that it goes both ways still. Yeah.
Okay, so then how do we make, so what we will want to make is a token event graph out of this. Boy, in all these years, I've never looked at one of these. Okay, this is kind of a good origin of life type system.
Okay, I'll keep a note of that.
No.
Well, let's look at the graph.
Yeah, but so what we want here is a token event graph. Okay, how does token event graph work again? We give it
rule, right?
Yeah, we give it a rule.
A list of rules.
And in our case, it's going to be a rule for rules, right? It's going to be basically a thing that feeds into string apply. Am I right? So it's basically going to be something that says the states, which will be called, let's call them S1, well, actually R1 and R2, they're both rules.
Yeah.
Which are both rules. So we can just say that here for now. This thing goes to string apply of R1, R2. Okay, so now that's that. So now we start this off from this thing here, if I'm not mistaken. Now, how does token event graph? Does it allow multiple uses of one initial token?
We have to say token multiplicity.
Okay, so what do I say? Token multiplicity is all?
Automatic.
You know, it is very easy to get very complicated stuff for these kinds of systems. Oh my gosh, what the heck is this thing? That's crazy. That A goes to AA in like 2 steps produces this giant mess. All right, let's just look at one step.
Well, one step's going to be underwhelming.
Except
A goes to AA, A goes to AA. AA goes to AA. Wow.
Okay, let's just try something much more straightforward. Let's just try this. Let's see what happens to this after 2 steps. Why are there so many events here? How can there be so many events? What are all those events?
Nick, do you know what those events are?
Well,
like what?
Oh, I know what it's doing. It's doing, let's see, can we deduplicate the events? Yes, we can. It's just applying itself. It's just because, well, let's see, just string apply. String apply doesn't do a union. Or does it? No, string apply does no union there. That's why we're getting a bunch of these events, I think. So if we say event deduplication.
Yeah. True.
Then, okay, that's more civilized. So A goes to B leads to that becoming B goes to B, which in turn, okay, that's nice. All right, now let's try the case.
Should we do A goes to AA with event deduplication?
Yeah, we can do that, but let's do A goes to AB. Okay. And let's try doing that with graph layout. Goes to layered digraph. Why is that not putting the A goes to AB thing as the yeah.
I don't know, because it has.
Nick, do you know how to do the root vertex thing? The thing where it says root vertex goes to whatever.
So maybe you just like graph layout list of where the graph embedding and just root as an option to that. Root vertex.
Is that what it is? Root vertex?
I'm not sure, but I think it is. I'm gonna see. I'm gonna check. I can try.
Yes. You know, if anybody ever believed that simple programs could not lead to complicated behavior, they should try. Just crazy what can happen. I mean, A goes to AB gives that crazy thing there. Okay, why are there so many events? Well, I guess it's not surprising there are lots of events by the time you've got. So this is already pretty interesting that we can get. So we apply rules to rules. And, all right, so let's try to understand what we get from applying rules to rules. And by the way, here, we could, let's see, we could do the same thing with let's do this with two-way rules. So let's write out string apply for two-way rules is this followed by, okay, so first of all, it's not rule, it's two-way rule here. Do we need to canonicalize by flipping the two-way rules around? Is that something we do?
Is it? Nick, do we do that?
I maybe, yes.
Well, should we?
I would think so.
Okay.
But it probably happens as part of the canonicalizer. But we don't have a canonicalizer here because we don't have blanks.
Yeah.
Right.
Okay, but what we need here is the corresponding thing with the flip around of LHS1 and RHS1, correct? Can we just keep doing this in the tuples? Is that the right thing to do, or is that not?
You mean put the flip in the tuples as well?
No, we shouldn't do that. We should just join the tuples to the other tuples, correct?
So
Nick,
you have
are
another,
you following?
you have another tuple for the flip, and then you join that with the original one.
Yes.
Yeah.
And then this one is RHS1.
Goes to LHS1.
Yeah.
Yeah. Okay.
Okay. Now, supposedly all we need to do, if all of our technology works according to plan, is change that to a two-way rule.
Come on.
No. Failure. Okay. Let's see what happened here. So this, so let's say, what's that?
What, Nick?
I was just wondering how's the edge count 0? So string apply return an empty list.
Well, oh, look, here's the problem.
All right.
Types bit us. Let's just ignore the types.
Okay.
I bet you could just do it with substitution lemma, some clever rule.
The same thing.
Patterns.
Yeah. No, I have no doubt. I mean, because we can do that. Okay, so this is the two-way rule there. So now let's try 2 steps in the two-way rule. That's remarkably similar to the one-way. I see the one-way rule has less elements there because it doesn't have the AB. The two-way rule has A goes to A there because it substituted AB goes to A. Okay, so let's try. This is so insanely, kind of trivial yet non-trivial. Why did that not? Oh, because the root vertex is probably not okay. Let's do that. It's interesting that the structure looks very, very similar to this. It doesn't seem to care what the letters are.
I think it's the same.
Yeah, because it's always the same character at the same position. We already had those examples.
How do we get a token event graph without the nodes? Do we say token labeling are a false?
Yep.
All right, I wonder what this looks like. Can we get rid of the, let's see, does it make sense to do token deduplication as well?
I think it's on by default.
It's the default. Yeah, I was going to ask.
I see.
True by default.
And we're already out of range here.
Yikes.
Okay, so in this case, okay, so if we say vertex list here, and we then say select cases of that underscore two-way rule.
You can just do it as a second argument to vertex list.
Come on, I didn't know that.
Yeah. I do it all the time.
Wow, that's very convenient. Okay, so now let's look here at, let us do the following. Let's say string length, map string length onto that at level 2. And let's replace two-way rule by list. Okay, and then let's say list plot. I suspected as much. It's basically filling in all the cases. And if we did something where we said A goes to AAA, it would end up, it's some number theoretic problem, what it fills in.
Nice. Interesting.
So we can also do theorems in this case, right? We should be able to use essentially your find proof function on exactly this graph, shouldn't we, Nick?
Yeah.
The fact that we get reflexivity without putting it in the rule seems to be really important. We get A goes to A, AA goes to AA. Seems important.
Well, I think we have put it in the rule by the fact that it's a two-way rule.
The point is we still have to entail it.
Yes.
Like it's in the entailment cone. It's not the node, it's not the seed.
Right, I understand. That is interesting. Yes, I agree. That whatever you start from, I mean, okay, so I guess the point here is whatever you start from, you get reflexivity.
Yeah.
That is an interesting point, because I wonder what else, whatever you start from, you get.
Aha. Well, welcome to mathematical rheology, right? Yes.
I wouldn't call it reflexivity though. It's not variables, just constants.
Oh.
But it's still, they act as variables here because they're able to go into any piece of this.
Yeah, just very specific.
Right.
Okay. Yeah, we'll put in air quotes.
Okay, so I mean, obviously the question is, do you get integers, for example? Do you inexorably get integers from this?
Wow. How much interpretative license do we have, you know?
I don't know what it counts, but obviously this isn't a very convincing integer. Okay, let's go back to what Nick had originally been doing here, where we're establishing a proof.
There's our point. Yep.
And by the way, can we use the same basic rules? What are the rules here? AB goes to B. Let's just try that. I think we've already seen that here. I just want to see what that, I can't imagine it's going to make any difference. All right, what's that? Is that the analog? How close is that to the 2-level version of this?
I think the only difference is that you don't have parentheses there for the strings, right?
Yes, I think that's right. That it assumes associativity, basically.
Yeah.
So there are fewer nodes. Actually, I mean, I don't know. These are just both complicated pictures, and it's not clear they look the same. Oh, that has the whole
Can we
root
get a
vertex
root
thing.
vertex for the other one?
Yes, we can. Although it's tricky to get that root vertex thing.
Right.
But if we stop doing the root vertex for this,
Well, okay, right. Still,
I mean,
slightly different.
it's similar, it's different, I don't know. They're not quite the same.
Mhm.
Yeah, because of this associativity and this after flattening of the string. Because our center, if center dot has an attribute, flat attribute, that would be the same.
Yeah, okay. Well, let's do that. Let's make this set attributes of FF to flat. Okay, and here we just say FF what is that compared to? That's to be compared. What's that?
Yeah, and also you have to replace patterns with symbols because A blank, just A.
Well, I know, but why isn't this picture the same?
Why what?
Why isn't this picture the same token event graph that we got in the case of
In what case?
in the strings case?
Well, that's what I'm telling you. It's because it has patterns. A pattern, B pattern, and B pattern on the right. So it basically can apply to any sub.
Oh, I see.
Not just B.
I see. So so if what we did here was we made those A and B.
Yeah. Still something not right.
By the way, I wonder how much of what we're doing we should actually look at with the non-pattern case. I guess it becomes non-trivial in the token event case. It's not very non-trivial. Well, in the ordinary case, we can still get subtrees, right? So let's take the example of, for instance, the thing I was using as my main sample thing. Let me just do this. So let's say we pick oh, I see. If we say AB here, that is trivial. And why is that trivial? probably it's obvious that that has to be trivial. Yeah, without patterns, that's not going to do anything. But if it was in the token event type model, it might do something. And in fact, your values of substitution lemmas should be the same thing as what we're doing up here.
Do you want to check?
Yeah, but actually what I want to check before that is I want to check this with AB goes to that with the literal there. What the heck is that? Why is that dead? Okay, what's the difference between a string?
No string.
Oh, I see. The problem is that this has binary elements. The string has the extra degree of freedom that it can slice into itself anywhere.
Yeah, you have to add some triple blanks.
Right.
Left
But
side.
the extra feature that they can be spliced at any point. And that's what we don't have here. Whereas expressions with binary operators can only have subtrees, can only have quotes predefined subtrees extracted. Right, that's the difference.
Yeah, you can make like an example above it, FF flat simple, to make it more like string.
What do you mean? This?
Yeah, it's like your rule should include some triple blanks that you splice back, and I think it should still work. Like F triple blank, AB triple blank, A.
Just the triple blank or an X triple blank?
X,
you have to splice
because
them back.
you have to put it back here. So X triple blank, comma, Mr. Comma.
And then what? Then over here, I would say FF of X, B, Y, right?
Yeah.
Except I need the triple blanks. I cannot imagine your equipment is going to handle triple blanks without snarling up inside. But let's try it. I'm going to be very impressed if this actually does something useful. Okay, so what did that do? Okay, what on earth is this doing? Are you claiming this is like the strings case? So you're claiming that structure. Oh, look, you might actually be right. Look at this, look at this, look at this, look at this. Okay, hold on. This case is, so token labeling is false. Okay, there we go.
That's what it looks like. Yeah, okay.
Well, wait a minute. That's yet different. Okay, where was the strings case? Token event graph of eq. Where's the case for strings? Let me find the case for strings up above. Yeah. Okay, we can do the strings case now. Okay, that's those things. Now what we want is AB goes to B. AB goes to B, no root vertex stuff.
Do 2?
Yeah. So 2 and token labeling is false.
thing still has some extra thing.
Indeed, it does. That's to be compared with this. Okay, let's do a little bit of ruleology on the rules on this case here. Okay.
Okay.
How do we make this not a token event graph but a multi-way graph? Is that easy to do to remove the events?
No,
What are we
just
going to call these things? What are we going to call these creatures? Ruleology of accretive. It's not really string substitution systems, but it's not really right. It's not really right. It's really self-applicable. What is the right term?
I mean, is it? Are they not accumulative?
I meant accumulative here. Accumulative, but they are accumulative, but they're also really, this is string rule substitute. It's you're substituting string rules.
Well, that's fine. I think string rule sounds fine.
No, it doesn't. It's a very long name. I mean, we might as well call it Azarus or something. Okay, all right. Let's just look at
yeah. For we'll come up. We'll wordsmith it later. Yeah.
Okay. So all right. So let's look at all possible cases because we can just enumerate these, right? We can just say let's see. So what we want is how do we want to do this? We want to say tuples. We're going to get pairs, basically. Tuples from I think we have a resource function. Okay. All right, so we want table of that I, let's just say I up to 2. Although we also probably want the null string, now that I think about it. That's also a case we want to consider. Okay, so let's flatten this. Okay, so that's a group of our possible substitutions. And now let's say tuples of that, comma 2. Okay, and let's just say now we want to apply two-way rule. Okay, that's a very unprofound. That is an unbelievably bizarre. That's the thing where you were talking about yesterday. Yeah, you were talking about this. This is your uninhabited.
Well, this is kind of computability itself, perhaps. Oh wow, look at that. Well, it's not the uninhabited type, but it's that you can have a mapping between empty types that itself is constructible. Anyway, yeah.
Okay, well there it is, but there's the animal, and it's okay. So now let's try here. Let's get rid of that. Well, do we want that? Do we want it? Let's not do that. Let's just say this, and let's say labeled arrow that, this, that, and let's give it a try. Maybe we'll regret this. 2 steps. Could get very weird, but let's try it.
This is.
I love the null string goes to null string. That could really go badly.
This looks okay.
It does look okay.
Wow, the null string go to null string is
is a thing.
It's an event. It's just a token and an event. But it looks the same as A goes to A. It looks the same as that reflexivity for A. Huh. Look how complicated the null string goes to A is.
Yes.
What?
We need to understand that.
What?
Okay, so there are basically a couple of different types here.
What is this?
So A goes to B. Let's look at A goes to B more carefully.
How does string replace flops with empty string anyway? Does it like insert itself into between any character?
I would assume so. All right, so A
Oh yeah, it is. Yeah.
goes to B. Let's have token labeling on. Okay, is that the end of the line? Because there are 4 things there and it's never going to do any more.
I don't. Yeah, I don't see what else you could get. I mean, you can increase
You're just
the
going to
traffic.
get more.
Yeah. Right.
Yeah, you're increasing the traffic because you're doing token multiplicity, which we need.
Yeah.
Right. Okay. Okay, so this is a pretty good model for sort of absolutely minimal mathematics, now that I think about it.
What do you mean?
Strings applied to string. It's better. It's an upgrade to the NKS version of string axiom to string. Anyway, okay. Let's take a look at A, B goes to B. All right. So let's look at the case.
Blank goes to A. My goodness.
Well, let's look at that one. That one is pretty weird. I'm sure it's the same as A goes to blank. You gotta be kidding. That's just ridiculously complicated. Okay, so what's happening here? So this is, how does it manage to produce? Oh, I see. It produces A goes to A because it takes the blanks around that A and it puts A's in there.
Yeah.
This is definitely making something from nothing. Okay, so this is presumably, okay, so it manages to generate the blank goes to blank rule. I suspect it's going to generate everything goes to everything. I think it couldn't fail to. Yeah, it must generate everything goes to everything. But it does so in a very entangled Rooleadal way.
Yeah. Yeah. Ex nihilo. Right.
Yes.
Yes.
Well,
Hey, if only
in the beginning,
philosophers
there's
had a
just an
computer,
A.
man. Well, no, in the beginning, there's just blank.
Yeah, except there's also a rule that talks about A. I mean, it would be more impressive if blank goes to blank made something, but it doesn't.
Well, but from blank goes to blank, you at least get a token and a rule, right? And then
Yes,
from
that's
there,
true.
you can work it. So the fact that you get something, wow. If only the philosophers had computers hundreds of years ago.
Yeah, well, right. If Leibniz had actually succeeded in making the thing he wanted to make, then he would have concluded many things. All right, so this is, well, what is that thing? I mean, what is that? What is that? There's got to be an easier way to represent this. Each one of these is a pair of numbers. And those pairs of numbers, I'm pretty sure this is a token event graph for a, yes, it's a numerical multiway system where, look, this is going to be the same thing as this. Okay, we should be able to start off with 1, 0 here. And what this is going to do is it's going to take each number and it's going to add, it's going to go, what is it doing? It's adding and subtracting 1. from either side, I claim.
That's kind of how I interpreted it. Yeah.
But it can't go below 0. So let's write out what it actually does.
Okay.
So I think it goes from 1. Let's say it goes from 1. And here it's taking those two things. And it is, let's call this N1 and N2. And it is making from those what is it doing? It's taking those two things.
Why did you remove the two-way rule?
What's that?
Why
No, I
did
don't
you
think
remove the two-way rule? Like with the 0.
What do you think we should be doing? I mean, I think we're going to get, go ahead.
You need a 0, actually, because it's like there are two independent ways you can substitute. Use the numbers on the left and right hand side. So you need a pair. You either add 1 to the left hand side, add or subtract 1 to the left hand side and to the right hand side, but not below 0. And if you have another rule with different numbers, you use them instead of 1. So you subtract by given number when you combine your rules.
Yes. Well, I'm just wondering whether we can get something somewhat analogous to this by pure addition. Okay,
with the vector, yeah.
Well, I'm saying without a vector, with just whether we can get something somewhat analogous by just saying it's. I think that this is range. Let's see, what is it? It's from N1 minus N2. It's from the range of the min of N1 minus N2, N2 minus N1, I claim, and that minimum of those and 0 range to max to N1 plus N2. This is my claim.
Okay.
I admit that doesn't look very similar, but I'm not giving up yet. Oh, why has that got to negative numbers?
Negative, yeah.
Wait a minute, it's min. Do I need the max here? I need a max here.
Okay.
Okay, so now we keep going. Humph. All right, well, I admit that doesn't look very similar, at least not given that it's lining up all the ones and zeros there, and it's just making some kind of ladder. It's not making a ladder, though. It's making something more like this, I think.
Yeah.
I don't know why it's...
You need a vector of two numbers.
Yeah, to get this exact thing, I agree, you need a vector. Yeah. Well, okay, let's write out what the thing is with vectors, okay? So I think it's the same thing, but just with vectors. All right, I don't think it's super interesting. I don't think it's going to be very revealing. I think it's going to be, what I was wondering was whether it was directly equivalent to, I mean, it's similar to a system based on with numbers. Although it's an interesting case because I didn't study yet. I just mentioned some stuff about the token event graph case of systems based on numbers. That's still to be studied. And this is a simple case of that.
Mm-hmm.
All right, zooming out here. Let's see, we hadn't tried applying your proof yet to these things. So let's try doing that. So let's say we've got A goes to, all right, let's see, proofs on strings. Okay, so now we're going to apply your proof system to the AB goes to B string. Okay, so we've got this, and now we say vertex list of that, comma, blank, two-way rule. Okay, so there are some theorems. So pick a theorem. Let's pick.
B goes to A, B. Yeah.
I do like that one. Or should we do B goes to AB? That's a fun one.
Okay.
Okay, so now, Nick, how do we do the proof?
You find proof, give it a graph, give it your list of axioms, and this theorem. Yeah, basically that initial condition. The second argument. That's it.
Like this.
Yeah.
Wow, that's cool. Okay, now how do we draw that as a subgraph? So now we say subgraph of %380, comma that, right?
Yeah.
Why is that so trivial? Oh, because it is. There's event 42. Yeah, okay. So now if we say graph that vertex labels to automatic, well, there we have it. Beautiful. Beautiful. Now let's get a less trivial theorem. Okay, so let's run this another few steps. Okay. Now we have a ship like we had before. Now we want to now let's see, we want to say vertex list of that two-way rule. Okay, pick your theorem.
Well, let's find one that is less trivial. Let's see.
Somewhere in the middle. It's like big one. Yeah, like this one.
As opposed to I rather favor this one. I don't know why, but I rather favor that one. So if we say find path, find shortest path between in RGG3 between the axiom okay, well, I don't, is it necessarily, okay, so let's do the find proof in RGG3 of the axiom but now the proof, this is really beautiful. I mean, this is just like find equational proof, except its arguments are in the opposite order. Possibly because find equational proof has its arguments in the wrong order. Why is that so trivial again? When in doubt, one might say, not to coin a term, but ruleate, so to speak, as in, let's just run all the cases.
Something weird happened. I don't like the result.
You think it's wrong?
Yes.
Well, this, let's just take There are non-trivial cases here.
Yeah, but that particular one is kind of weird. I don't
Well,
understand.
how do you know AB goes to B? How the heck can it get in one step to this?
Yeah, right.
That's why Nick's saying he doesn't like the result.
Looks.
So I understand that it could get it in one step by shortest path, but defined proof should also include all the sub-proofs of all the input hypotheses into events, and they're missing for some reason here.
Okay, this looks like a bug then.
Yes.
But we have non-trivial proofs here. Now, does find equational proof work with strings? Does anybody remember?
This is a resource function. Find string proof or something. Yeah, find string proof. By Jonathan.
Okay. All right. So then find string proof of, so let's see, what's this one here? This is probably, that's probably proving, unfortunately, we rather stupidly didn't give what the cases were here. But that proof there should be, do you think it's this? Do you think it's proving this?
Well, that looks like the sink, right?
It does look like the sink, yeah.
Yeah.
Not even kitchen. Unlike this, the Rouliad could be viewed as the ultimate kitchen sink, so to speak. Never mind. Okay, so find string proof takes its arguments in the order, presumably, of find equational proof.
Yeah. Well, just a rule, not plural. So I guess you need
equals.
Oh, actually, it works with two rules. And look, I'm just looking at the example. It works with two rules.
Is this? Oh, is this an identity? Oh, it already got the answer there. Are these all identities here? Well, that one clearly is not an identity. And that one clearly is not. So let's take that one there. So what is that proving then? Let's take this as its result.
Two-way rule instead of equals. No, it should work with two-way rule.
It's not going to work with equals actually because
it evaluates.
Yeah. What's that? Yeah.
Because it evaluates.
Okay, now what's this? That's a proof object, but now let's say proof graph of this.
Okay.
Why did that not work? Why did that not work?
No, it's I know what's on it. It's a new prototype thing. If you just replace string logic with, I don't know, equational logic inside proof object, then it would work. It just doesn't support the string logic thing.
Nice.
Okay, so the point is this is actually working in a different way because this is trying to prove true. Right?
That's how it works, right?
Yeah, that's how it works.
Yeah.
So that's where the notion of truth comes in, which we don't have right now. This is trying to take the axioms and the hypothesis and turn them into a self-evident identity.
Yeah.
Now, how would we do that? How would we flip this around to do that? I don't know why we'd want to do that particularly. Maybe we want to do that if we're obsessed with logic, but there's no particular reason to do that here. This is a perfectly valid proof.
Yeah.
Where the proof involves, so every event, so we could write this proof out. Let's write this proof out as a piece of kind of, as a piece of math where we take each event, right? And we're taking the events here. And okay, so let's write out, let's say this proof, okay? Let's say writing out a proof. So we've got this, and now what we want to say is for every event, we want to write what its output and its input are, I believe.
Okay.
So what we want to do is we want to take this and we want to say, let's call this, I don't know, GG PG equals this. Okay, so now what we want to do is we want to say, for every one of the events there, so we want to say vertex list of GGPG underscore list, that will be the events. And so for each of those, we want to get their vertex. Okay, so here's what we want to do. We want to say vertex in component in GGPG of that. And then we want to say arrow vertex out component PG, that whole thing mapped over vertex list of this, and that whole thing in a column what? Oh, I want to do only one level of vertex in. What is it called when it's why does the event go to itself?
Wrap your one with list, so it's exactly one.
Oh, I see. I think that was a bug that I. Okay, that is almost brilliant. No, except it isn't. I would expect the in component to have two elements going into the event. Why doesn't it?
No, it should. It's like.
Well, but look at this graph. It doesn't have it.
I know. But find proof tries to do it at least. It's just that's why I have this function extend graph or something, because token when graph drops some edges, right? So we can extract it from using subgraph, but the proof may contain it actually.
But look, what we expect here is something which is a form pair of things come in. I mean, we want to write this out as a proof, because if we did find equational proof here, so let's take this thing up here, okay? Okay, what is this doing? This is going to show a result like this, and it's going to show it, right, it's going to show the rule applied to that input expression gives that output expression, right?
Yep.
by virtue of the substitution lemma. So something's wrong here, which we need to debug. But we should be able to get a kind of a manifest of the proof in which we basically say, in which we have a thing which says, rule blah 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 applied to blah 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 gives blah blah blah, right, for every step. And with subscript, the rule is applied at position blah blah blah, right? That then is the full proof, because that could be written as string replace. Then the proof becomes string replace part of blah 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 blah, right, of that with a rule at a particular position. So the whatever it is, so the function that is the proof is a series of string replace parts. Am I right?
Right. It sounds
okay.
Sounds fine.
So basically what this is telling us is this is now a model for what's happening in mathematics. These things here, wherever they were, things like this creature, is a low-level model. I have to say, I mean, the obvious thing to do now is do the exact same thing for hypergraphs. Why have we not considered that? So in other words, what would we do if we wanted to apply hypergraph rules to themselves? Right, so
okay. Mm-hmm.
Because in hypergraphs, we would typically have a rule like, xy, xz goes to, whatever it goes to. X, Z, XX, Y, Z, W, XW or something, right? That would be a typical rule. Okay, so what we're now saying is, how would we insert a rule into a hypergraph? Because then we're going to use the hypergraph to bootstrap itself. Am I making sense? Because usually we have code and data being separated effectively there. And what we want to do now is we're can
codifying
the
the data. Yeah. Right.
Yeah. Can we make the universe made of not, instead of saying, find the rule for the universe, it's like the universe is all rules and they're just applying to themselves.
Mm-hmm.
Okay, so how do you make a hypergraph? I'm kind of guessing that this is trivial. I'm kind of guessing all you do. Yeah, I think all you do, look, here's how you do it. You just have we can call it an attachment atom, a link. I think that's right. I think all you have to do is to say there's a link there, link X, and this has to have link X as well. In other words, so the way we're thinking about this is, okay, so alternative view of strings. What we could do is, instead of having A goes to, one view of strings is A goes to AB. Okay, but another view would be AX floating in the soup with XAB.
Okay.
And then what happens is the meta rule picks up linked pieces. Now, the ugliness here is that every one of those needs to, but it's not really that ugly because every one of these is a new atom of space. Every one of those links is a new atom of space. In a sense, here we have a special hyperedge that is it could be a unary hyperedge, which is the link hyperedge. So for example, if we were to, let's just make this explicitly, this would be a if I'm not mistaken, just this. Okay. And then does it matter that that's disconnected? So I think what we want to say is vertex labels Is this right, or do we need to do this differently?
A little bit differently. Right now you have like, your link is not connected to the hyperedges.
I know.
It's just, yeah.
Well, for strings, okay. The string analog, okay, for strings, let's write it out for the one we need for strings. So there, I would claim it is simply A, B, link X. And then this, that's not a map, it's just an apply to this. Link X goes to B. Huh? Am I wrong again? Yes, I'm wrong again. I'm wrong again, I'm wrong again. Each one of those is a free floating creature. Right. Those are the two things. It's a little odd. I mean, we then have a meta rule that picks up links and uses those as the rules. Am I making sense?
Yeah.
Well, doesn't like Wolfram model supports it? Like a specific named atom.
Yeah, I think it does. But remember, it's not a single named atom because every time you generate a new rule, you have to generate a new link atom.
Well, it doesn't support like a pattern at least.
Probably. By the way, we should stop calling these things atoms. We should call them eames.
All right.
So is it a linkeme?
It's a linkeme.
A link-on? Yeah, okay.
No, it's
a linkeme.
An
L-eme. Yeah, okay.
Right.
Figure it out.
So we can say it's a linkeme. Because okay. So essentially what we're saying is, right, the basic point here is there are many ways to make the raw material here. And the way we've been talking about, we've also been talking about using combinators as the raw material.
Mm-hmm.
There's a question of actually, do we need to do that? Or could we be using, I mean, the feature of combinators as raw material is that they record, they reproduce the tree structure. And we can clearly represent those with some kind of Polish notation in hypergraphs, but it's a little icky. However, any of these things work. You know, we've clearly got a very low level, I mean, okay, this is, okay, the analog analogy. What we've got is combinators or, Wolfram model rules is like machine code, I claim. Whereas, whereas I've got another crazy analogy here. Whereas our string rewrites or what are we calling them? Our symbolic systems are like an assembler.
Well, sure.
In the sense that what's happened is, in the assembler, there are still names for things.
Yeah.
Whereas in the machine code, it really is pure data, so to speak. So the compiler, in a sense, axiomatic mathematics is the assembler. We can go to the machine code that's even below the assembler after, what is it called? Oh my God, I haven't thought about these things. One of you, what is it? When you go from the assembler to the machine code, it's not just the linker, because that's just one operation. I guess it's loader. Is that right?
Oh dear.
Who knows this? Does anybody? Nick, do you know this stuff?
No, not really. Well, linker, I understand.
Yes, right. But there's a thing that goes from, I think it's the loader that goes from the assembly code to the machine code. I should know that, but and it probably had a different name in British English.
Well, it's not a software thing. It's hardware thing. As soon as you have a CPU instructions, then it's your processor is working into binary, right?
Yeah.
So it's like, because machine code is your binary things, so it's like.
Okay, but in any case, so I mean, what we're saying is the sort of high level mathematics. That's kind of fun that the axiomatic mathematics is the assembler, and then high level mathematics of the kind people actually do when they're not using formalized systems is So the basic point is, in the assembly language, you're not yet, at the machine code, at the true machine code level, you can do sort of generic science, just like we can do in the physics project. At the assembler level, you've still got all kinds of named things floating around. So basically what we're talking about is, can we make, identifying, high level constructs, from the machine code is reverse engineering. That's what we're trying to do. We're trying to do the analog of take your random piece of C code or something that has been compiled into machine code, not even assembler, machine code. And reverse engineer it and figure out what the so what you're trying to do there. Actually I should right. In reverse engineering, you are trying to identify. I think you need to identify sort of repeated lumps of functionality in much the same way that we need to find integers.
Yeah.
So essentially what's going to happen is, we have our sort of soup. What we've got basically is the compilation down below mathematics and physics looks like things like this, except they're very big. And we should probably work out, here's the thing we need to do, an estimate. Oh yeah, this is actually interesting. Okay, estimate the size of mathematics. And how big is it compared to physics, right? So what we know, like in MetaMath, for example, we've got a few 100,000. Okay, so in rough, so how far? So MetaMath is like an assembly. It gets down to assembly language, right? That's a fair statement, Nick.
Yeah. Well, yeah.
To assembly, not machine code.
That's correct.
Yeah.
Assembly.
Right. So how much further does it need to go? So basically, something like MetaMath or Lean, is the equivalent of assembler. So to get to machine code, we're going to need to take every identifier and represent it in binary, in quotes, in binary.
But not in binary, in emic, right?
Yes, in emic, in terms of eames. And that is a weird word. Yeah, I guess that's right. I guess that's what it is. It has to be represented in eames.
Yeah.
So
basically, now you're in releological territory. I mean, you're in releological territory when you're doing the symbolic systems in MetaMath, but it's even more releological at the machine code level because some of it doesn't necessarily undergo definitional entailment into anything that's named. And there's all kinds of, I mean, look, there's plenty of room at the bottom. At the emic level, there's all kinds of stuff that doesn't even make its way to.
Yeah, that makes no sense to humans.
Yeah.
In the current state of
or
humans.
Potentially any observer,
Well, we don't. Yeah, that's right. That's the question. Is what they.
Yeah.
Okay, so.
That's another good question, actually. Right.
So you think it's called emic, not emery, for binary?
Emery. That sounds like a university, doesn't it?
Yeah, I guess so. Because I do think that the level, the analog of it. I mean, emic. The problem is that there's two different names. There's the name for the level of things represented in eames, and there's the level of things at the level. So there's the equivalent of the atomic level, so to speak. And then there's the things you can make out of atoms, right? There's the.
Oh, I see. Just to say the like eam dynamics, basically something.
Yes.
Yes.
Eam level. And so what we've got here is, an eam, a fundamental, what the heck do we call it? I mean, it's a fundamental element is what it is, a fundamental element with a distinct quotes UUID, for want of a better. Okay, so then there's the question of the emial. I'm not sure that's the right word. There's the level, which is, that level, and then there is the thing that is the set of things you can make, the language of things you can make out of eames. Which is a little different. I mean, this is like saying, okay, so the analogy here would be, this is like a morpheme or something. And this would be like, there isn't really, it would be sort of almost like the morphological level.
Mm-hmm.
And this is morphology. Or what is usually called morphology, although that morphology tends to be the study of the morphological level, not the set of things you can make at the morphological level. Which of course leads us to emology, but that's a different.
Okay.
What's
the difference between emology and basically machine level? That's just machine level releology, though, right? But it's really, it's releology.
No, that's the rules. Those are the rules.
I mean,
that's rules, not the dynamics of what can happen. That's the rules at the eam level, right? As opposed to the what can happen at the eam level.
So let's say you're looking at clouds, eam clouds, little machine halos. I mean, what would you call this? Is that the study of the rule? Is it the study of the eam?
No, it's the study. Okay, the dynamics of clouds.
Yeah.
Of eames.
Mm-hmm.
I mean, there's several levels here because you have to go above to get to things which you can identify as mathematical statements. A mathematical statement can contain many eames.
It has to.
Right. It contains lots of eames. It might
Yeah.
be compiled into its machine code. A mathematical statement might be, the Pythagorean theorem might be, well, we should estimate it. I'm going to guess it's 1,000 eames. Maybe it's much bigger than that. Maybe it's 1,000,000. I'm not sure. I'm going to guess it could be, no, it's probably bigger than 1,000. It probably has to define its language. It's probably like 10,000 eames.
I mean, some of the clouds that are involved before you even get to the symbolic level, those clouds could be dense, that would be my guess. If it's something that human mathematicians kind of got for free early as physical observers, right? I imagine that those early observables correspond to quite dense machine clouds. That's just my guess.
Well, much as the same way that space requires that you need a lot of atoms of space to make a piece of space.
There you go. Right.
Right. So, okay. So the claim would be, at a low level, there may be lots of eames to create math ideas that are obvious from our physical experience. Like the notion of the things in geometry and so on. Okay, just as lots of eames of space eames, so to speak. Oh my gosh, that's going to space eames. The question is, should that be space eames? That doesn't really work, does it? That might work. It's actually not a terrible word. I mean, it's the alternative to atoms of space. Okay, lots of space eames are needed to build space. Okay, so now I want to estimate the size of mathematics. So we have in mathematics on the order of, let's say, 5 million theorems that people know.
Oh, I see. It's mathematics basically up to, well, here's the thing. Do you mean mathematics up until present? Because if you want to do that, then there has to be mathematical time. If there's no mathematical
I'm
time,
saying mathematics as it exists. Look, math as it exists today versus, let's say, the region of physical space that we've explored. Although that's a complicated thing because we've got photons and so on. And we're not even discussing yet what the analog of particles is in mathematical space. Although my guess is the analog of particles is robust concepts. I mean, in fact, probably the analog of particles, so here, analog of particles is probably mathematical concepts, robust mathematical concepts.
But what's a concept at the machine level, right?
Well, I'm saying it's a topologically stable thing. Like the number 2 is represented as some bizarre cluster of eames that are somehow stable and propagate through and survive. In other words, the number 2 survives proof, so to speak.
So it has to kind of accrete at the machine level. It has to be dense enough, but it also has to be, it has to have what I call proof fitness. It has to survive proof. Both of those.
Yes.
Yeah. Okay.
But so I still want to estimate the size of mathematics, right? So we got, let's say, 5 million theorems that humans have done. So humans have explored a certain region of physical space, and more with photons and so on. And in that region of physical space, in round numbers, there are, let's say 10 to the some number of hundreds of atoms of space. The slice of the Rouliad explored by humans, let's see, have we estimated that?
How could we estimate it? I'm not saying it can't be done, but what's the approach that you've taken so far?
Well, I mean, to estimate. Okay, here's a way to estimate it.
Okay.
You are, okay, so clearly there's a Reulial cone, Reulial light cone, which is essentially and we have not, just like we are not expanding, our civilization is not expanding at the speed of light in all directions, right? Our civilization is rather modest in its expansion rate relative to that, to put it mildly.
Yeah.
So similarly, our expansion rate in Reulial space is also rather small. I mean, our expansion in Reulial space has to do with essentially exploring new ways of understanding how things work.
Abstraction.
Yeah,
right?
it's some form of abstraction, or some form of, not really abstraction, but some form of paradigmatic change. So, I don't know how big our sort of zone, and that's a hard thing to estimate, right? We don't know what the set of all possible abstractions is, or the set of all possible, and we don't know what fraction of. It's just like we might ask the question. Okay, so another question is, what fraction of mathematics have we explored? So just like we have an idea of what fraction of the physical universe we've explored, and it's let's see, how big is it? It's around, what is one? Let's see, one astronomical unit divided by radius of the universe. Oh boy, that's pretty small. That's pretty embarrassing. So we've explored on the order of, I mean, give or take, we've explored 1 part in 10 to the 47 of the universe. 1 part in 10 to the 46 of the universe, physical universe, by visiting it. It's a little different what we've explored through photons, with the light cone of photons. But so now the question is, what fraction? And that's, by the way, that's in physical space. So in branchial space, there's even some tinier fraction, and in Reulial space, it's even a much, much tinier fraction. That's probably 10 to the 10 to the 1 part, and 10 to the 10 to the 100 or something. The universe is pretty big, really. I mean, especially when you include more than just physical space. But now, I'm still very curious. What, if we think about sort of what we've discovered in mathematics versus what we've discovered by, in physical space, whether we can, because we should be able to have a comparison. I mean, we can count the number of eames of physical space that, let's imagine we're doing our astronomical unit thing. We could say, this is 1 astronomical unit divided by, let's say, I wonder whether we actually have something for the elementary length in here now. Probably not. And let's say 10 to the minus 93 meters. Oh, great, thank you. It's all to arbitrary precision. Okay, 10 to the 104. So that means that is so the number of eames, is what I would guess, around 10 to the 300. So, and that's just including physical space. If we include branchial space, it'll get multiplied by a factor of 10 to the 120. If we include Reulial space, we have no idea. That's much huger, a completely different order of magnitude, 10 to the 10 to the something. But so what that's telling us is,
I'm not sure I entirely understand this estimate.
So this is the number of atoms of space contained in 1 cubic astronomical unit, based on our estimate of the elementary length.
Based on the, okay.
which is probably wrong, but is at least, maybe roughly right, within a factor of 5 of exponent. But okay, so that means there are that many EAMs that we have, explored in the physical universe. So the question is, how many have we explored in the mathematical universe? In all of our 4 million theorems proved in the history of mathematics, how far? Clearly, those theorems, like our spacecraft, don't explore every piece of that cubic astronomical unit or whatever.
Oh, definitely. Yeah.
Right. We just explore little pieces of it, just like in mathematics, we're only going, we just do particular theorems. We don't do other theorems. So we're just going, we're visiting particular places. And so then the question is, roughly how far have we probed? Yeah, this is something we should be able to estimate in some way, at least roughly within, I think it really depends on how far down. Right now in the Pythagorean theorem, for example, these formalized math systems are using about 100,000 assembly language statements to get that. So the question is how much further do we have to go to get to machine code below the assembly language?
Right. We want to know what fraction we've probed, but we also want to understand the nature of that which has not been probed and whether or not any of it is non-trivial.
It will be, for the same reason that
parallel, perfectly viable mathematics, for instance. Right.
Well, I think that's very much like saying, if we go to another solar system, will it be the same? I suspect that the translation from arithmetic to, from geometry to algebra is similar to motion in metamathematical space. That's like us going to visit another solar system, where some of the same principles apply, but there are details that are different.
Mm-hmm.
So, if you ask how many,
but the translation cost would be high potentially for a parallel system. Yeah, that's the point.
It's like we spend,
that's the motion,
n generations
right?
in an interstellar spacecraft.
Right, you have to get in a generation shift, right, to go from one to the other, right?
I think that, right, and our way of making that translation in mathematics is, if we do it at a formal level in formalized mathematics, okay, this is where, category theory claims to explain the structure without filling in all the details. But again, it won't be actually useful because there are things you're not going to be able to figure out from category theory. You can figure out, you might be able to figure out that the law of gravitation still applies to the solar system, but it doesn't tell you whether it's a pleasant place to live on planet 7 or something.
Right. Nor does a morphism tell you the transport cost to get from one place to another.
Well, that's true too. Right. And it's just saying, right. Anyway, well, okay. Nick has been very silent, which probably means he's writing code. And,
yes.
Yes.
Did you figure out find proof thing?
Not really, but I'm trying.
Can you see that it's a bug, or do you not know yet?
It's a bug, yeah.
I think it's okay. It's a complicated function. All right, we should probably wrap up, even though there's so many things I would like to study here, and I think, yeah. Well, this is there was some comments on our live stream. Let me just look at these for a second.
Much philosophical discussion of the Roolead. Should tell ask Hatem to take a look at these comments, maybe.
Since observers are essentially the convergence of quantum systems, they should be critical joints in metamathematical space. Look, the analogy between quantum mechanics and metamathematics is for next week. I mean, I think that
well, we've discussed this before.
We have discussed it. We have discussed it, and what we need to see now that we understand. Okay, so one complexity is that we've talked about proof paths, but in this version of proof in token event graphs, they're no longer paths; they're subgraphs. So apply homotopy type theory to what is the analog of homotopy theory in the case where we're not talking about paths anymore. Right, so we need
you mean you don't
homotopy.
You mean you don't have continuous deformation anymore?
No, we have continuous deformation, but it's for subgraph to a subgraph, not a path to a path.
Well, do you still have a path over the subgraphs?
No, but I mean, what do you mean? You have, look, we're saying a proof at the token event graph level is a subgraph.
Yep.
So I'm asking you, you need to continuously deform one subgraph to another. Now, in traditional homotopy, done with continuous spaces and so on, you're really looking at paths, that is one-dimensional parameterized families, not subgraphs. I don't even know what the analog, what a subgraph is, what the limit of a subgraph. Okay, the limit of a path in continuous space is a path. It's just a one parameter, position thingy, right? But what's the limit of a subgraph in continuous space?
Good question.
Right. I mean, the subgraph, perhaps it isn't even a surface. It's not even close to that. It's much more fragmented than that.
Right.
So
exactly.
In what is the analog? I mean, homotopy type theory, you are looking at, actually don't know, how does the continuum limit type thing work to get you to actually something that looks like ordinary homotopy, or does it never get there?
The continuum, well, you just use the interval usually, right? Interval from 0 to 1.
For what?
Like have A cross the interval from 0 to 1 mapping to B. Something like
Sure,
that.
sure. No, I understand that. For in the continuum space case, I'm asking in homotopy type theory, where the homotopies are between
Spaces.
I mean,
yeah.
What's that?
Yeah.
But those are discrete.
No. I mean, you can have a path between points, but then beyond points, you have
the analog of morphisms, I would assume.
You'll have one space, a two space, etc. However, there are like these trees in homotopy type theory, and I haven't fully kind of investigated. That would be something maybe I could ask Xerxes about.
Right, but I mean, the category theory also does not discuss, to my knowledge, I mean, it's really talking about morphisms. It's not talking about sort of graphisms of some kind. That is, it's looking at mapping from one object to another.
I mean, you can have a category of graphs.
I understand, but that's a different thing.
Right. Yep. Right.
What I'm talking about is the actual structure of morphisms.
Yeah. Right.
Is no longer this maps to this, but some kind of more complicated graph. As opposed to, I mean, I think that's the monoidal. I don't know. I mean, because that I'm not sure. Anyway, William is asking, can mathematics be reduced to something purely syntax, string substitution, etc.? Yes, that is what we think. It is reducible purely to eames, a giant bucket of eames. And our interpretation of the number 3 is, it's similar to our interpretation of a piece of space. The fact that we interpret sort of all that giant collection of atoms of space as a oh yes, that's a meter in length, is kind of as it's the same level, it's the same kind of human interpretation type thing that's going on for these eames at the bottom of mathematics, so to speak.
Right, but the other important point is that when you get to that bottom level, and there's plenty of room at the bottom, by the way, you're going to also find all kinds of foreign, strange syntax, which might not make it to familiar mathematics.
Right, and the aliens could have chosen a different slice, and they could be happily doing mathematics that is utterly incomprehensible to us.
Right, but with this method, we might be able to, by starting at the machine level, find something like that. I mean, it would take, the whole point is it involves computational work to find. Yes. Because now we are doing metamathematics in a way that's not purely just a kind of inheritance from what we get as physical observers. We're using experimental computational metamathematics to actually employ computational work in order to find, potentially parallel.
Well, right, but I mean, what's
systems.
happening is we've gone below the level that we slice out of the Roolead to get physics. And below that level, all bets are off in terms of our intuition from physics to apply to mathematics. We're doing it at a much baser level. And Taka here asks what the relationship of all of this is to why is metamathematics important? How does this relate to the model as a whole? Basically, because what we are discovering is that physics and mathematics are fundamentally the same thing. And that discovery is important because just as we can import all the things that have been discovered into physics into the foundations of mathematics, so we can also import things discovered in mathematics into physics. And that's not just at the level of, we can apply this equation, but at the level of totally fundamental level of saying, what is the foundational structure and how does it apply? And that's, I think, the main important. Plus, it's also pretty interesting after all these years to know what mathematics actually is.
When you say all these years, you mean like thousands of years, right?
Yeah, I mean thousands of years. Yes, I mean since Plato, basically. I mean, because Plato talked about these. I mean, Plato was concerned with this issue of whether there is a real there for mathematics, or whether it's and then later on with Hilbert and so on, it became very much this kind of idea of you can just write down whatever axioms you feel like. And what this is telling us is, well, you can write down whatever axioms you feel like, but they may not be what, there may be all kinds of problems with them that make them totally unsuitable for human consumption, so to speak. And those axioms that we didn't pick might be ones that are, might be great for the aliens who have a completely different sensory system and a different intuition about the world, but not very good for us.
Yes, but that's the whole point, is that we're no longer just mere physical observers. We have tools that we didn't have before. And very interesting to see what we're capable of understanding and finding at this point.
Right. Okay, there's one more comment here from Anders. Roolead is all possible rules. Are there also sub-Rooleads, equivalence classes? Yes, there absolutely are sub-Rooleads. And in fact, one of the interesting things is that I'm pretty sure that one of the things that will happen in mathematics is, insofar as mathematics does not have time, mathematics is, whereas physics does have time, is important in physics. It is a different, what we're getting in mathematics is a different it's a different way of sampling the Roolead. Anyway, we should comment from Rob here. It's weird how much of this is analogous to stuff in developed symbolic mythological systems. Yeah, I have this feeling that, I mean, this is one of the terrible things that a lot of these ideas about kind of structure and sort of symbolic structure of things, these same ideas are going to occur everywhere because they are just fundamental ideas about symbolic structure. And, that's why in another, I don't know how long it'll be, a few weeks, months, or whatever, I'm hoping to really try and analyze, I've already started, kind of how our project relates to the history of philosophy. And many of the things that show up are things that have occurred in the history of theology as well as the history of philosophy. They're kind of arguments about the universe, humans, the relation between those things. And many of these things are kind of universal facts that are sort of universal facts about symbolic systems, so to speak. And I fully think that there's a level of kind of unification that we're beginning to get to. And I think it really helps. This exercise of seeing if we can understand mathematics as we can understand physics is a very useful exercise, which seems to be progressing quite nicely. And I hope it doesn't mean, I've been writing something, and I hope the conversation, I don't think there's too much that I'm now on like my 5th iteration of the introduction to this thing that I'm writing. And unfortunately, because I tend to be a sequential writer where I just write once, I don't go back, and after I've got to the end, go back and change the introduction. So I kind of have to know what the point is from the beginning. But I think I don't think that there's too much here that, I mean, the only thing about the thing I'm writing is that I hope people will survive through the somewhat technical middle of it to actually get to the various punchlines at the end, because I don't think it's good to give the pure sort of philosophical ending without explaining how you get there at a slightly more technical level. But anyway, it's okay. Well, I should go off to my next thing, but thanks all, and thanks to folks on our live stream for their various comments and questions, and to be continued as we try and make little tiny motions in Rullial space to see if we can understand more kinds of ideas. All right, okay, I gotta run.